we're talking about relays. What do relays do? Let's go ahead and go over what we've learned, and then we'll apply how this relay controls the air conditioner. Let's start off with L1 and L2. We're gonna go a little more in depth now. Now we got the basic low voltage diagram. Now we're gonna go back through it piece by piece and then fill in a few things. First thing, L1 and L2. Both bring in 120 volts. When they come into the system, they come in on what's called a terminal block. So our terminal block is what brings L1 and L2 into the air conditioner. So let's go ahead and start with getting 240 volts to the primary side of our transformer, because that's how we get the 24 volts that we are seeking. But our primary needs 240 volts. So let's do that. L1, L1. Let's go over, bring our line, connect. 120 volts. Transformer says, hey, I'm halfway there, I need 240. So let's bring L2 to L2. Bring this down, crossing the line, make your half loop bridge. Very good. Come down and connect in over here. Primary side has 240 volts, 120 on L1, 120 on L2. Now we're gonna produce 24 volts. We got our 24 volts, we go to our secondary side, then we use colors. As we discussed, 12 volt common is going to be blue for the purpose of our diagrams, and 12 volt control, red. Let's start with control. We agreed before that 12 volt control will only go to the red on the thermostat. So we'll go ahead and bring this down, over, and up. As we discussed in our Survey Monkeys, heat sequencer gets the white wire. The white wire goes to the heat sequencer on the other side of control to give it 12 volts of low voltage. In this case, as we discussed earlier, we're going to make what on the diagram is called a key. When you have to put special information in, there's always going to be a key. Every diagram is going to have a key. And we're going to fill some of the key out tonight so you see exactly what we mean by it. So first things first, white is going to be purple because we can't see white very well. So you draw yourself a little square and then put, so you see purple equals white. So purple is our white wire. Now the key will tell anyone that's reading the schematic, and you'll come across many keys yourself, it'll tell you extra things about the diagram. So let's go ahead and complete our control side, because we already know where the common is going. Let's go to our control. We agreed that white is going to be purple. Here's our white, not our green, not our yellow, not our orange, not the common, but the white. We're going to drop down with our purple wire, which is white. We're going to bring it all the way over. Then bring it up to the control side of the heat sequencer. Now we see our 12 volt control will stream into the thermostat. Homeowner says, Mr. Thermostat, it's cold in my house. I need the heating elements. So Mr. Thermostat says, okay, you've asked for heat. I will send your 12 volts into the white to activate the heat sequencer and activate the heating strips. Would also send, if that's the case, it's going to send the 12 volts through the green as well, so the green can turn on and the inside fan motor can turn on, because we need the fan motor along with the heating element to give us heat in the home. Okay, so let's head on over to our common side. 12 volt common. What did we learn? Every relay has two hands of low voltage, common and control. Two hands. I don't even gotta say it. Put the common in my hand. Common right here, common right here. On the secondary side of the transformer, we're gonna come over and just drop right on down. This is a very clean diagram because we're only doing one relay and one high voltage part of the relay. So we can see very well. So we got our 12 volt common coming into the common side low voltage of the heat sequencer. So now when Mr. Thermostat says turn on Mr. Heat Sequencer, we're going to send the voltage. What's going to happen is, as we discussed in heat sequencers, what there is there's something called a bimetal. It's like, it's almost, if you imagine just a T that's inside of there with 2 points on it. So when you get 24 volts across the bottom of the heat sequencer, this T will slowly rise up through the both stages, and then when it does, it activates and it closes this circuit right here. Because normally power can get in through here, but it cannot exit through here until there's 24 volts to the bottom of the heat sequencer, and then the bimetal will float up, and then the circuit will continue and close, and then power can travel through. So let's understand exactly how the sequencer turns on the heating element. And for that, we got to go back to 240 volts. As we discussed, the transformer needs 240 volts to give us 24 volts. The heating element also requires 240 volts to turn on and heat the home. What does this mean? Well, if the transformer needs 240 volts, it needs a leg from L1 and a leg from L2. If the heating element also needs 200 volts, it's also going to require 120 from L1 and 120 from L2 on this side. So let's see how this works. I keep stressing to you about common, and common is everywhere. Common and control are on the secondary side of the transformer. Common and control are also on L1 and L2. So let's designate a common. When I say designate a common, you know exactly what I'm talking about. I designate L1 as common. So I'm going to go up here, and I'm going to write common. So I know that L1 is the common for the 240 volts. So we have a common side here, and that means that L2 is going to be control. Just as the secondary side of the transformer has common and control, L1 and L2 also have a common and control side. Let's see how these two tie in. Once you tie in the common and control for the high voltage, then you understand the whole diagram, how the low voltage works with the high voltage. Okay, so if we designated a common on L1, let's bring power over. We need 240 volts to turn on this heating element. So what does common do? If we look common here, common provides a constant 12 volts, if you will, to this common leg of the heat sequencer, which lets us manipulate the other 12 volts through the thermostat to give us 24 volts. The same concept applies for high voltage elements. What that means is we have a common. Just like the low voltage has its common leg, put the common in my hand. Well, guess what? Mr. Heating Element is saying the same thing. This is my common, 120 volt leg. This is 24 volts we're dealing with. Now we're talking 240. We're talking the element, what actually creates the heat. But a common is a common is a common. So we have common on the high voltage. Let's go ahead and let's get that drawn in so we get a better understanding. We're not going to use blue and red because that's for the low voltage. We're going to go ahead and use our pen. So common to L1 and common here. So I'm going to come up and I'm going to bring 120 volts to this heating element at all times. There's 120 volts. Now this heating element has a common 120 volts. Just like Mr. Heat Sequencer says, don't play with my common. You give me my common, Mr. Transformer, every time I want it. Every major high voltage component has a common leg to L1. So this way you know that the heating element will always have a common leg on L1. Meaning that the fan motor, other components in the air handler will also have a common leg. So let's see how the heating element works. We're going to bring in the common 120 leg volt. So Mr. Heating Element says I have half of what I need. If I have 240, I have 120 all day consistent, no interruptions. because you always put the common in my hand, whether we're talking high voltage or low voltage. Common in the hand. So now, let's see how we get voltage to the other side of this element and activate it. So L1 is our common. That makes that L2, 120 volt, is our control. So now if we run this 120 all the way to this other side of this element has a constant 240 volts. It's always going to be on. The point of having relays in a thermostat is to control high voltage. So what we're going to do is we're going to take our 120 volt L2 control, we're going to drop it down, we're going to go over, and we are going to drop into the top side of the heat sequencer, one of the legs on the high voltage side. So now follow the flow of electricity. Electricity is leaving L2 and it's stopped right here because this bimetal will be down if there's no 24 volts. So what we do is on the other side, we add our wire all the way through and we bring it to the other side of the heating element. We bring 120 on L2 control through the heat sequencer, the high voltage part, to the other side of the element. This way we can turn on the element when the sequencer gets its 24 volts, raises the bimetal, closes the circuit, and then the other 120 volts can flow through. And now this heat element is on and it's heating the house. When we tie it into this, what do we see? What is a relay? I say again, a relay is a relay is a relay. A relay controls high voltage, controls this high voltage, and what does it control it with? Low voltage, 24 volts. And remember, 12 of the volts are already at every relay. We're only shuffling 12 volts through the thermostat to turn on when we want to close this relay, bring it up, close the circuit, and turn on the heating element. Now that you understand common and control, a constant common to the heating element, if it has 120 volts, the heating element will not turn on. It's only when it receives the other 120 volts and receives a complete 240 that the heating element turns on and heats the home. So imagine this. Imagine if we did not have a heat sequencer or low voltage. Imagine if we had this heating element only. So if we only had that heating element, what we would do is we would take L1 common, don't play with the common, over to the one end of the heating element. And then what would we do with the other end of the heating element for the control? We would take it all the way down into the thermostat. So if we didn't have low voltage, we would have to run the control leg of 120 through the thermostat, exactly how we do the red to jump to low voltage. We would have to do that with this portion right here. And that's why we have low voltage, because that way we can use 24 volts and a relay to open and control the circuit. That way we only send 12 volts through the thermostat. If not, you'd have 120 volts and homeowners would be electrocuting themselves. Because as soon as it's the equivalent of taking the wall plate off your wall and sticking your finger in there, is if a homeowner pulled the thermostat and started touching it. So this is the heat sequencer in action. Let's go ahead and go through our diagram and learn a few more things. We learned that L1 and L2 are called the terminal block. We learned that every diagram is going to have a key to tell you that the purple is white. Well, this is the first diagram that we've done that has both low voltage and high voltage. So we have to notice something, that when we're dealing with the diagram, there's a difference even in the size of wires. And what I mean by that is this. You see how these wires are just about the same distance, the same thickness. Color pencil's a little thicker. But on a real diagram, what you're going to see is you're going to see that high voltage is extremely thick. Very thick wires. This is done on purpose because just by glancing at the actual diagram, you can designate the thin wires from the thick wires, and you can see that, hey, this is a low voltage wire because it is so thin compared to these much thicker wires. So your diagram is going to have to show this as well, that your high voltage wires, which is anything that comes off L1 and L2, are thicker on the diagram. See how much thicker these are now? So, and this has to go through all the way through here, because this is a high voltage wire. Much thicker than the low voltage wire in the diagram. And the key will reflect this. We will write this in the key so anyone looking can look at it and see the thickness in wires and understand what is high voltage and what is low voltage just by looking at it. And any diagram that you look at now, you're going to notice that you have thicker wires that go through the diagram and much thinner ones. And that's the reason why. Because your high voltage wires are always going to be thicker. See? Much thicker than our thin low voltage. So what we do in that case is you write on your key and you take a thick wire, just like that. Make it just as thick as the wires in the diagram, or get used to seeing it equals high voltage. And then when you see a thin wire, because in the field you're not always going to see colors. You're going to see you'll see a black, but it's going to say red on it. It'll say red on the diagram, so you understand that's a red wire. So in that case, your wires would be thinner for the low voltage, equals low voltage. So moving forward on your diagram, try to have a key. When you draw your diagram, draw a key, because you may want to take your colors in there, and purple should always be white. And then you can designate what is high voltage and what is low voltage. As you can see, it looks very clean. We're going to go ahead and do this with every relay, every high voltage component of the relay, of every relay, and then put it on the board together. So hang on, it's getting interesting now.